Welcome back, everyone, for another hypothesis testing video having to do with population proportions. We have here in the year 2000, wow, such a long time ago. It must have been before you were born, which is amazing to me, but it's I'm not particularly old enough to be like the old man talking about back in the day or whatever. But we had 58% of females aged 15 years or older living at home. That seems like a pretty small number, and it's kind of, well, I guess depending on how many 15-year-old females are living alone, it's kind of, why would you choose 15? But anyways, that's according to the U.S. Census Bureau. A sociologist tests whether this percentage is different today by constructing a random sample of 500 females aged 15 years or older and finds that 285 are living alone. So what we're doing is using a previous number, which was from, and that would be something that was familiar for us whenever we were talking about sample sizes, is that you could use a previous survey that had taken place in order to get your point estimate. But in this case, this sociologist is testing whether this percentage is different today. So notice not whether it's greater or less, only whether it's different. So they're testing whether the proportion is different from or else is not equal to 58%. And this sociologist tests against the original survey, which stated that 58% of them were living at home. The question here is whether there is sufficient evidence at a significance level of 0.1 to conclude that the proportion has changed. So this alpha level is 0.10, and the critical value for that one, I keep having to derive the critical values again, which is no problem because we have the inverse normal function on here. In this case though, oh wow, we should be careful not to make such a mistake, because in this case when it says not equal, that means we are using a two-tailed test. So that will change the critical value for us. Now, what we should do instead of what I just did is to come to the inverse normal, and in fact we want this area of 0.1 to be evenly split up between the two tails. So we want each tail to have an area which is half of that. We want the area here to be 0.1 divided by 2, which is 0.05. So I actually want to find the critical value that way by making the area to the left be 0.05. And I'm sorry that I keep doing that zooming thing. Here we have 0.05 as the area on the left. And that will get us a different critical value, which is here. This critical value is going to be plus or minus really 1.645, because we want to have the positive one is here, is 1.645. The negative one is here, negative 1.645, because z-scores are symmetric around 0. Now, we have a test statistic which is going to come from our calculator. Whenever we come in here and we go to stat and then go over to tests, we're talking about proportion, so it's a one prop z test. We're testing the p-naught value is 0.58. In our survey, we found out that 285 of such females were living at home, and that was out of a survey size of 500. And we're testing whether it's not equal. So let's calculate that one. Not equal. So in that case, we find a z value. It is negative 0.453. And if we draw that on our picture, this is the value negative 1.645. I just don't, well, I'll write it. I'm just trying not to get it mixed up with the p-value. That's negative 1.645 is there. Ours of negative, it's almost negative 1/2, so maybe that's about here. This is our test statistic that we found, which is this Z. And it's not inside of the critical region. We also have that the p-value is 0.65. Wow, it's a large probability to get such a test statistic, 0.65. And that's greater than the level of significance, which was 0.1. So we should not reject the null hypothesis. And if we come here and we form a conclusion about that one, we would do the familiar one about there is not sufficient evidence to conclude that basically that the proportion has changed, that something that maybe we could say here that the proportion of females aged 15 or older who live at home, to conclude that it is different than, I think is superior English grammar. I hope you guys will help me out here, is different than 58%. And here it's just necessary maybe to cram as much of the context of the problem and as much specificity about the claim as you can. So we would want all of the stuff about aged 15 or older, living at home, all of that. Now, we have here some supplementary questions that says, are we supporting the claim? Have we found statistically significant results? In this case, we are supporting the claim, really, that the proportion of females who live at home is 58%. I think that our evidence would support that, or at least our evidence certainly does not give us any support to the contrary. So it's a bit of a, I hate to answer these questions like a politician or whatever, but what about this question? Have we found statistically significant results? Our results, you notice that the p-value, which is the probability to get that test statistic, was 0.65. That's 65% chance. That's not statistically significant in this case. Statistical significance, by the way, if you remember, it has to do with the level of significance, which was in this case 10%. So if we were less than 10% chance, it would have been statistically significant. Let's move on though to the next example. It says in 1990, it was reported that 47% of households had a gun. In a survey conducted by the Gallup organization in 2000, 395 out of 1,012 adults said they had a gun in the house. So we're assuming that somehow by just surveying adults, that we ended up with some type of a random sample and that everything is good on that front, because we don't really talk about the sampling methods and stuff like that. But Gallup organization, I think Gallup pretty much has random sampling down packed, so we don't have to worry about that. It says, is there significant evidence to support the claim that the proportion of households that have a gun has decreased since 1990? So we're testing whether actually the proportion has gone down or else that now it is less than 47%. So the null hypothesis is the default one, which is that it basically is the same as it was before. In this case, we have significance level is 0.05. And since it's a less, then it is a left-tailed test. So we should use the same critical value as we had before, which was negative 1.645, if I remember correctly. I'm pretty confident about it. In this case, we will resort immediately to the calculator to carry on with this problem, because calculating this test statistic, it just happens so much more easily by going to one prop Z test. And we're testing against the null hypothesis, which is that the proportion is 47%. In our survey, we had 395 people had a gun in the house out of the 1,012 who were surveyed. And we are testing whether the new proportion is less than 47% now. So we're testing whether it's less than the null hypothesis. because we want to see if it has decreased. So now we can see that our test statistic, which it's a tongue twister trying to say that one, that's what the TS stands for, of course, is test statistic. And Z for our case, our test statistic is negative 5.07. So if we draw a picture of this one, we were doing a left-tailed test with the critical value of negative 1.645. And so this is our critical region, is this tail on the left side. And we got a test statistic which is very small. It's kind of over here or something. I don't, if we go like 1, 2, maybe it's here. So this tail, it just keeps coming this way and it's getting very small. But here's our value, is here for our sample that we took. It's well within the critical region. It is so far in the critical region that there can be no doubt. And what was our p-value? This is a small p-value. Do not ignore the e negative 7. That means 1.9 times 10 to the negative 7th. I will write it that way, 1.9 times 10 to negative 7. So there must be, what, 6 zeros in a row? And then the 1 9? That's a very small probability. We should reject the null hypothesis in this case. This is less than our level of significance, which was 0.05. So how are we going to word that one? Let's think about it very carefully. We're going to reject the claim. And so we will say there is sufficient evidence to conclude that, what are we concluding? We are concluding with the context of the gun ownership in the households, sufficient evidence to support the claim that the proportion of households that have a gun has decreased since 1990. We found evidence to support that. So we want to basically copy and paste this part about the proportion of blah, blah, blah. There is sufficient evidence to conclude that the proportion of households that have a gun has decreased since 1990. And I hope it's clear what I mean by all these dashes. It's what I said for this sentence, and we can, of course, reconstruct that sentence using the template that we had from before. But anyways, we basically supported the claim. We found statistically significant results. There's no doubt about it. That survey was very significant. Now, there is only, let's see, really one more example. So I think that we have time to do it. It says, in clinical tests of the drug Clarinex, sounds like it's maybe for allergies or something. It sounds like it's a spin-off of Claritin. It's the Chinese version. It says 1,655 patients were treated with 5 milligram doses of Clarinex, and 2.1% of them experienced fatigue. I know that a lot of people get fatigued by taking Benadryl. I definitely don't, which I find to be a blessing. It says use a 0.01 significance level to test the claim that the percentage of Clarinex users experiencing fatigue is greater than 1.2%, which that was the rate for those not using Clarinex. So whoever was on the placebo, they were feeling fatigue at a rate of 1.2%. And we're testing whether Clarinex, basically this would be the structure of a clinical trial where they're trying to figure out whether Clarinex, whether you could say that one of the potential side effects is fatigue. You need to find a significant difference between the people using it versus the people not using it of who has fatigue, because some people are just going to be fatigued anyway, or else there's, the placebo effect and all of these kinds of things. But in this case, What are we dealing with? We're testing whether the proportion is greater than 1.2%, which of course is 0.012. We're testing whether the proportion of people getting fatigue is more than this, and so the null hypothesis should just say equals 0.012. The alpha value in this case, it says use a significance level of 0.01 to test the claim, so this one goes 0.01. I cannot remember what the critical value should be for that, so I will just, as usual, just come back to inverse normal. It's so convenient to find the critical values. In this case, by the way, we're testing greater, so this must be a right-tailed test. Excuse me. In that case, we want the tail to be on the right, but we understand that if we find the critical value that's on the left side, it's just going to be the negative of the true critical value. I hope it makes sense that we should use 2.33. And the test statistic in this case, let's go ahead and find it. Of course, after step 2, going into step 3, that's when we go ahead and run our test on the calculator. We're going to one prop z test. No big deal. We are testing against the value of 0.012. And in our trial, there were 1,655 patients, and for this value, maybe, I hope it's not going to mess us up, it didn't actually tell us how many people were fatigued. It only said it's 2.1% of these people, so we should go ahead and calculate that x. It's going to be 2.1%, which is 0.021 times the number of people. This will give us 2.1% of the patients. So 1,655 times 0.021. How much is this? It's 34.75. Maybe we can just call it 35 people. We should probably round up in the event that there's no such thing as 0.755 people. And we will use this as our x value whenever we do the test. And here we will go to one prop z test. X value is 35 out of 1655. And we're testing whether it's greater. So let's check. Calculate it. The test statistic is the z value, of course, is 3.418. I'll just round it there. Oh, excuse me again. Now, the picture that we're drawing is of this bell curve, and I don't want to get it started too low. We are testing for greater, so it's a right-tailed test. It has alpha value 0.01, so that means that this critical value here of the z-score, this threshold between the critical region and the non-critical region is 2.33. We found that one. Our test statistic, it lands inside of there. It's over here. It's the one that goes like 3.418. It's inside of the critical region, and we found also, in the meantime, the p-value, which goes times 10 to the negative 4. It's 3.16, I'll say, times 10 to negative 4, which goes with 3 zeros in the front, and then 316. That's a very small probability. That's less than our alpha value, which was 0.01. See, we even chose a 1% level of significance because we really did not want to make a type 1 error in this case, because it's a clinical trial. You know, people don't want to be fatigued by this medicine that they're taking in case they operate heavy machinery or something like that. They don't want to fall asleep driving the bulldozer. And we actually found a statistically significant result over here because we want to reject the null hypothesis. Do you see why? We can, from a classical perspective, it's because our test statistic was in the critical region. From a p-value perspective, it's because the probability to get this test statistic was less than the level of significance. And so we would say that there is sufficient evidence sufficient evidence to conclude that, and we want to test the claim that, and kind of from that point, test the claim that, and then we want to just snip this part and pretty much insert it over here to conclude that, and then I will call this star. We want to put star over here in our sentence. There is sufficient evidence to conclude that the percentage of Clarinex users experiencing fatigue is greater than 1.2%, which is the rate for those not using Clarinex. So probably in the commercial for Clarinex, you're going to see when the guy starts talking really fast, explaining all the bad things that can happen to you if you take Clarinex, one of them he's going to mention is fatigue for sure. So that's the end of this one. We see here a little bit of a description about if you have a two-tailed test, that making a confidence interval is relatable or is somehow analogous to doing a two-tailed hypothesis test. And so you can, in the case of making, for a two-tailed test, making a confidence interval, if the P0 value, which is the value from the null hypothesis, if that is inside of the confidence interval that you come up with, then you will not reject the null hypothesis. If it's outside the interval, then you will reject. So it's pretty straightforward doing that one. And then this is something that we mentioned before, the difference between practical significance versus statistical significance. Statistical significance, we claimed that that would be just any result that was significant based on the level of significance that we chose based on the alpha value. But, when it's talking about something that doesn't make too much sense, like, we're testing whether the proportion of M&Ms in a bag are green is more than 10% or something. It doesn't really matter. It's kind of like, who cares? That would be a low level of practical significance. Practical significance is a type of significance that's really going to affect people's lives. We're thinking about, the side effects for the drugs and stuff like that. If one of the side effects of a drug is death, and you find a statistical significant chance that the drug is going to kill you, then that has a lot of practical significance. But when we're talking about M&Ms or the number of females living at home and stuff like that, it's really kind of meh. And it also, you notice some of the time, it really, the value can be borderline, where it's like if the alpha value was 0.05, but then the p-value that you get is like 0.049 or something, it's just barely inside of there, or in the context of the critical region, if you get a value that's just barely, it just skates into the critical region by the hair on by the skin of its teeth, as it were, it was so close to being outside the critical region, then the practical significance, we would just say cold scientific mindset, yes, we will reject the null hypothesis in this case, but we would be careful about the conclusions that we make, because it really wasn't that significant. Maybe if you're way over here in the critical region, then we'd be more confident in general about making some kinds of claims. In the case where you have it's statistically significant but not really practically significant, you might want to do some more tests or something like that, or change up your hypothesis a little bit to try to get some results that are more meaningful. Anyways, I don't want to just ramble on about it. I hope this makes sense in general, but I know that you will get to do some examples about it. I don't have any examples here, but I think the homework has some. Anyways, thank you guys for watching these videos. That does it for 10.2. We will carry on talking about hypothesis tests for the mean a little bit later in 10.3. Thank you guys for watching. Have a great day.